So we're going to be working with convex lenses. And what a convex lens is, it's just a type of lens that causes light rays to converge. Convex lenses are also known as converging lenses. And what a convex lens does, it produces an image from the light rays. That image can either be upright or inverted, real or virtual, reduced or enlarged. And on the bottom here of the screen, I have a picture or an example of a ray diagram. So whenever you're trying to find that image, you have to use a ray diagram. So let's see how we make a ray diagram. The three things you have to have when you're making a ray diagram is your object, of course your lens, and your focal point. So the rules about working with a ray diagram is that one of the light rays goes towards your lens, parallel of your principal axis, through your focal point, and then you have a second ray that goes through your principal axis. So now we see that the two light rays meet up right about here. And this image produced looks a little bit smaller than your original image. So let's say it's reduced. This image is virtual and inverted over your principal axis. Sorry, it's kind of floppy. So it's reduced because it seems smaller than your original image. This image is virtual because this light ray right here was converged. So this image is also inverted because it's below your principal axis. So let's use another example, having your object a little bit closer to your lens. Of course, your object is right here, your lens, and your focal point. So, parallel of your principal axis towards your lens, towards your focal point, and then the second ray to go through that principal axis. And now there's kind of a problem because none of these two light rays are touching. So now we're going to have to extend back those light rays. So we just extend them back. And let's say they meet right about here. So the image produced is behind your object, and we can say that this image is, of course, enlarged. It's upright. And it's virtual. This image, of course, is enlarged because it's bigger than your original object. This image is upright because it's over your principal axis. This image is virtual because we had to extend back those light rays. So now let's see what our equations are. For your lens equation is 1 over dO plus 1 over di equals 1 over f. For your magnification equation, it's m equals hi over ho, or if you don't have hi or ho, you can use negative di over do. And what's really cool about this equation is that if you don't have your height or your object height, you can use the distance if you have your distance of your object or your image. So let's see what the variables represent. So for do, we know that do represents distance of object. Sorry, sloppy. And distance of image is for di. And your f represents focal point, or focal length. Magnification. The M represents for magnification. HI is height of image. HO, height of object. Height of object. DI, we know it's distance of image. And DO is distance of object. And for units, units have to equal out each other. So, let's try to have a scenario. And here's our scenario. An object is placed 15 centimeters from a convex lens with a focal length of 10 centimeters. Draw the ray diagram and describe the image. Find the location of the image and magnification. So first thing, let's draw out with our ray diagram. So let's say this object right here is placed 15 centimeters. And your focal point is placed 10 centimeters away from that convex lens. So I can't do anything yet, but because we have to find the magnification and your distance of object and all that stuff. So let's use the equations. So of course you have to use the lens equation. Remember, 1 over DO plus 1 over DI is equal to 1 over F. And your magnification, mag for short, is M equals HI over HO equals negative DI over DO. So now that we know what type of equations we have to use, let's give our givens. So, of course, we know that the object, your distance of object is equal to 15 centimeters. And we know that focal length, your F, is equal to 10 centimeters. We see here that both of these are in centimeters, so we don't have to change the units. So since both of them are the same, we don't have to do anything. So the next thing we have to do is solve. So for lens, we have our 1 over your DO is equal to 15 centimeters plus 1 over DI, which is what we're looking for, and 1 over F, which is your 10 centimeters. So subtract that 1 over 15 on both sides, and you're left with 1 over DI is equal to 1 over 30. Well, if we were to change this, DI is equal to 30. So now that we have DI, we can look for our magnification. And remember that equation is M equals HI divided by HO is equal to negative DI over DO. I didn't have DI to begin with. So now that I have it, I can just place it. So let's work with what we got. So 30, well, it's negative 30, divided by your DO, which is 15, and your magnification is equal to negative 2. So now, I can continue on my ray diagram. So, we know that the rules say parallel of your principal axis towards your lens. That lens converges it to go through your focal point. The second ray goes through your principal axis. And if this screen was bigger, we would be able to see the image. But since both of these since both of these rays don't touch yet, well, we can say we know that it's going to be 30. Your distance of your image is going to be 30 centimeters, and since here is 10, from here to 30 is where our image is going to be located at. So that's pretty much it, basically. So we know that our magnification is of -2. And we know that our DI is equal to 30. But looking at this so far, let's describe this image. We know that this image is going to be inverted. And it looks like this image would be a little bit bigger from your object. So let's say it's enlarged. And we know it's virtual because the lens converged this light ray. And there you go, congratulations. You solved your equation. You solved your scenario.